Hi viewers, welcome to Lama Solution. Today we are going to see about solar PV EV charging station with the grid integration in the MATLAB. This is a simulation model we developed for a solar PV EV charging station with the grid integration. This model consists of a solar PV array, and solar PV array going to be connected to the DC bus via this interleaved buck converter. And here you can see that this is a rating of a solar PV array. The single panel rating is 250 watts, and here we are using 16 series connected PV model in the single string. Totally it can generate around 4000 watts, that means 4 kilowatt at 1000 watts per meter square, and the voltage across that single panel is around 30.7, and then current of the single panel at maximum power point will be 8.15 amps. Totally here you can see 30.7 into 16, 30.7 into 16 is around 491.2 volt. At the PV power point condition, the voltage around 500 here. This voltage will be should be stepped down to 400 volt, because see here we are going to maintain the DC bus voltage equal, so 500 volt going to be stepped down to 400 volt. For that here we are using interleaved buck converter. This is structure of interleaved buck converter. Why we are using interleaved buck converter? When we are going to use normal buck converter, maybe go for a discontinuous conduction mode, and also the ripple in that load current, then output of converter and input current it have more. In order to minimize that ripple current, here we are using interleaved buck converter. When interleaving that two converter, then that ripple of current will be reduced. For that purpose only, here we are using this interleaved buck converter. And this interleaved buck converter will be controlled by means of MPPT algorithm. MPPT nothing but maximum power point tracking algorithm. The maximum power point tracking algorithm used in the PV system to extract the maximum power from the PV panel. Because here already I show that the detail. That means here you can see that for different irradiation condition, mean different sun intensity, sunlight intensity condition, what will happen that peak power of the PV panel will be vary. He must track that peak point. In order to track that peak point, we need to use some control concept. The control concept nothing but maximum power point tracking algorithm. Here this is known as maximum power. We are going to track that maximum power, that is known as maximum power point tracking control algorithm. In order to extract that control, extract that power from the PV, this interleaved converter, buck converter will be controlled by means of this incremental conductance MPPT. This incremental conductance MPPT receive two inputs, PV voltage and current. Based upon that PV voltage and current, here UT initialize 4 parameter: initial duty cycle, maximum duty cycle, minimum duty cycle, and then you have to calculate change in voltage and change in power, change in current, and then based upon change in voltage and change in current, you have to increment or decrement the duty cycle, as well as based upon that incremental conductance, you have to increment or decrement the duty cycle. This will be keep on executing not to find out the duty cycle for that interleaved buck converter, for step down the voltage from 500 to 400, as well as extract the maximum power from the PV. So next thing is grid integration. Here we have single phase grid. Here we are using 230 volt AC supply, and the 230 volt AC supply is connected to the DC bus, common DC bus via this inverter. In order to control this inverter, here we have that control logic. Here you can see that we are generating the current reference based upon PV current and EV availability, based upon whether EV is available or not. If EV based upon the availability of EV, we are going to generate the reference current. Here you can see that we are checking the PV current. If PV current is less than 0.5, that means there is no power generation from the PV and EV is enabled, then we have to charge the EV via grid. We are taking power from the grid. So next, for example, the condition will be changed from this point to this point. We are getting the power from the grid to charge the EV. When the power generation is more than 2 amps from the PV, then we are jumping from this logic to this logic. That means we are not taking any power from the grid. By reference, here we are making 0. Only thing you have to check that when PV is less than 0.5 amps and then EV is turned on, EV is connected to the system, then we are going to take the power from the grid. Otherwise, we are not taking any power from the grid. is directly the PV going to be used to charge the battery, not to avoid that cost of grid purchase. After that, here we are getting reference current, and then reference current going to be converted into sinusoidal form, and then here we are having alpha beta naught to dq naught conversion. Here we will have dq naught conversion. Next thing is, here we are measuring the inverter current. Here we need to measure the inverter current here, and then it going to be converted into dq naught by using alpha beta naught to dq naught conversion. After conversion of alpha beta naught and dq naught conversion, actual and reference dq naught going to be compared here and processed via PA controller, and then after conversion we are having controlled voltage in the form of a dq naught. Again you have to convert to alpha beta naught, and then you have to take this first quantity, nothing but alpha, and it going to be processed via sinusoidal PWM. It will be generate the pulse. So this pulse going to be is for control this inverter. The inverter, in this inverter when we control the current control concept. So next we have to move on that EV and EV and stationary battery connection. Here we are using bidirectional converter. This bidirectional converter going to be used to for connect the battery with the DC bus. That means we have to connect the EP battery with the DC bus, as well as you have to connect stationary battery with the DC bus. For that we are using bidirectional converter here, and bidirectional converter will be work on in both direction. To be send the power to the DC bus, or else it take the power from the DC bus. This bidirectional converter will be operate in both direction when a stationary battery is connected to the system. Otherwise, what will be when EV is connected? For example, if stationary battery is connected to the system. Oh, here we have some arrangement, both EV connected in the common converter. If stationary battery, that means EV battery is not presented in the system, then the stationary battery will be connected to the system. If EV battery is connected to the system, means stationary battery will be disconnected from the system. For that we have some logic. That means here we have circuit breaker. Here you can see that this is a control logic. That means if it is 0 means EV is not connected into the system. If it is 1 means EV is connected to the system. If 0 means it will be generate 0 here. It will be trip this circuit breaker, and then here we will have 1, and then it will be enable this trip. Then the stationary battery will be connected when the signal will be 0. Stationary battery will be connected to the system. Next thing is when here the condition will be 1 means this strip will be connected, and this circuit breaker will be disconnected from the system. Stationary battery will be disconnected, only EV will be connected in the system. When stationary battery is connected in the system, what will happen? This bidirectional converter will be acting both direction. That means when stationary battery is connected to the system, only the system will be operated. That means the people when we used to supply this local load as well as charge the stationary battery. When PV power is less, then what will happen? That the battery stationary battery will supply this DC load. Here during this condition, the grid never participates in the system. When EV is connected, that means this control signal is on, then EV will be connected with the system. During that, what will be happen? When PV having excess power, it will be supply this DC load as well as charge the EV battery. When PV is less than, then PV is not generating power, then the grid will be supplying power to the EV as well as this DC load. During this condition, when EV is connected, during that time grid will be comes to supply the power. This is a concept of solar EV charging station with the grid. And here you can see that this bidirectional converter going to be controlled by means of voltage control method. Here we are measuring the DC bus voltage and going to be compared with the 400 volt, and then it going to be processed via PA controller. So this PA controller then is going to be processed via PWM generator, and it will be generate the PWM pulse. So this is going to be used to for control this bidirectional converter. This will be control this DC bus voltage maintained at 400 volt. Next you have to test the system. Here we can measure the storage battery voltage and current, EV battery voltage and current, and here we can measure DC load, DC bus load current and power, and then here we can measure the power of PV, DC load power, battery and EV power, and then storage battery and EV one grid power, and here we can measure the SOC of the EV battery. The first one is SOC of the EV, and second one is SOC of the storage battery. Next thing here you can see the the inverter current and the grid current. Now the condition is we are connected in that EV. That means here we are making condition one. Now the EV is connected to the system. We have to check the response, and also we are varying the irradiation from 1500 and 0. Here you can see that the PV generating around 4000 watts. Here DC load is around 1000, and here you can see that the battery current right is around 12 amps, and then battery voltage is 250 volt. And here you can see here that power of PV is 4000, load will be 1000, and battery will be 3000. And the EV battery power, this is the pink color is EV battery power, and green will be storage battery. Based upon that power availability of PV, the power is taken from the DC load as well as but now the battery power for 500 watts per meter square, battery power is 2000. So that will be given to the DC load, and the remaining power going to charge the EV battery. Now you can see that PV power is goes to 0. When the PV power goes to 0, what will be happen? So we are getting power from the grid. Here you can see that we are getting power from the grid during this time. We can see that the EV battery is still in charging mode, and also DC load receive the power. Here you can see that when PV power change from 0 to 2000 watts. Here you can see that we are not getting any power from the grid, is goes to 0, and here you can see that EV battery is in a charging condition on. This is when we are connecting EV into the system. Here you can see that the storage battery current always 0, because when the EV battery is connected to the system, the storage battery will be disconnected, then it not taking any charge. So here you can see this variation of battery current, and here you can see the variation of DC bus voltage, DC load current, and DC load power. So this is variation of PV voltage, PV current, and the PV power. Here you can see that this is a variation of SOC of the storage battery. Here you will see that SOC will be keep on increasing for EV, but here you will see that SOC of that storage battery is very, that means discharging value is around 0.00001, like that only. Now I am going to change this control logic to 0. So now storage battery is connected to the system, and then you have to check the result what happened to the system and changing that condition. Now the EV is not connected in the system, EV battery. Now you have to check the results. Now here you can see that EV is not connected, that's why the EV battery current is 0, and then the remaining thing, the PV power voltage current will be follows, that is from 1000 watts per meter square to 500 and 0. Based upon that PV will be generate the power. So now here you can see that PV is initially 4000, 1000 will be given to the DC load, and 3000 taken by the battery. Now is 2000, 1000 given to the DC load, and then 1000 given to the battery. You will check the result when PV goes to 0. Now we can say that PV goes to 0, the stationary battery will supplying power to the DC load. It is going for negative. Negative in the sense here battery now comes to supply the power to the DC load. Here you can see that the grid is remains 0, because during when storage battery connected to the system, so the storage battery only used for supplying that local load. When EV connected to the system, so based upon PV power, grid will be connected to the system to supply the EV battery as well as the local load. This is a concept of this model. And here you will see that now the SOC battery will be remain at 9%, and then here you will see that that means storage battery first is charging mode, and then is discharging mode, again going for charging. Here you will see that you cannot see that 9% is that means charging it around 0.001 only, to minimum only is maintained at 9% only, because you can see here current of the battery will be 0 in all timing. So this is working of solar PV EV charging station with the grid system. Grid will be only connected during that when EV is connected for charging. Other time I won't connect to the system. Because of that, we will reduce the purchase cost from the grid. Thanks for watching our video. Kindly subscribe our channel and also click bell icon for notification about upcoming videos. Thank you. Thank you so much. Bye bye.